Okay. So this is the question, that is, suppose main memory consists of 32 blocks of 4 words each. Okay, 32 blocks are contained, and each block contains 4 words, and cache memory consists of 4 blocks. So it is very small memory, it contains only 4 blocks. How many bits are required for main memory addressing, and how many bits are there in each of, that is, tag, block or set, word, field of different mapping techniques? Okay, so this is the question. So what is given is main memory is of 32 blocks of 4 words each. Okay, so main memory consists of 32 blocks. Fine. So there are 32 blocks here, 0 to 31, and each block contains 4 words. This is main memory. Okay. Okay. And cache memory consists of 4 blocks. It is also told it consists of 4 blocks. Only 4 blocks are there, 0 to 3. And each block contains 4 words. If it is 4 words here, here also it is 4 words only. Fine. Now the first question is, how many bits required for main memory address? Okay, so it is told that it is 32 blocks of 4 words each. 32 is nothing but 2 power 5 blocks, 2 power 2 words in each blocks. That is, totally there is 2 power 7 words. Okay, that means the main memory is of 7 bits because it is 2 power 7. Main memory address must be of 7 bits. Okay, so that is the answer for first question. The second question is, how many bits are there for tag, set and word fields? Okay, so shall we go to the second question? I think there is no doubt in this main memory number of bits for the main memory address. Any doubt? There is no doubt. Okay, I'll move further. So that is in different mapping techniques, how many bits are required for in different mapping techniques. The cache memory will have how many bits for tag and block set and word field, whichever is applicable. Okay, so first one is direct mapping. Direct mapping contains the address. In direct mapping, the cache memory address contains 3 fields. Okay, word, block number and tag number. There is no set in direct mapping. Set block set contains only in set associative mapping. Okay, so first one is direct mapping. There is the address generated will be divided into those 3 fields. The total 7 bits will be divided into those 3 fields: word, block number and tag number. Okay, now how many bits are required for the word? Word is of, there are 4 words in each block. Okay, there are 4 words in each block. 4 is nothing but 2 power 2. So 2 bits are required for representing the word. Okay, next, number of blocks. How many blocks in cache memory? There are 4 blocks in cache memory. It is given, it is 4 blocks. Correct? So 4 blocks in cache memory. 4 is nothing but 2 power 2. Again, 2 bits required for representing the block number. Okay, so in 2 bits, that is 0, 0, 0, 1, 1, 0, 1, 1. I can generate this block unique addresses for this block number, for those blocks, isn't it? So 2 bits are enough. 2 power 2, so it is 2. Now tag number. What is tag number? It is, as I told, this whole thing is of 7 bits. this is 2, and this is 2. So the remaining is tag number. So it is 7 minus 2 plus 2. Okay, that is 3. Fine. So this is direct mapping. Tag number needs 3 bits, block number 2 bits, and word 2 bits. Okay, this is direct mapping. Next is associative mapping. So in associative mapping, you know the structure. The address, 7-bit address, which is generated for the main memory, has that address will be mapped to the cache memory. So how it is divided? Few bits will represent word and other bits will represent the tag number. So how many bits are required to represent the word? How many bits for the tag number? It is, word is 4 bit. There are 4 words in the block. 4 is nothing but 2 power 2. So 2 bits for the word. Okay. And the remaining bits are for the tag number. Total bits is 7 minus 2 is 5. Okay. So that is associative mapping. Next, what you have seen is set associative mapping. In the question, it's not given how many blocks consist of one set in cache is not given. So it is assumed that 2 cache blocks forms a set. Okay. So this is the structure of set associative mapping. Cache memory address structure is this one. Okay. So main memory 7 bits address generate agide. So the 7-bit address, how it is mapped in cache? First, the address will be searched in cache memory. Okay, so how it is searched? Means last few bits is for word, next bits is for set, and the next few bits is for tag number. So how many bits stands for the word? Word, there are totally 4 words in each block. 4 is nothing but 2 power 2. So 2 bits represent the word. Number of sets. How many sets are there? Okay. How many sets? How do you find the number of sets? Total number of cache blocks. Total number of cache blocks present. The cache memory consists of 4 blocks. Correct? 0 to 3. So 4 blocks are there in cache memory. And I have assumed that 2 blocks are present in each set. Okay. 2 blocks forms one set. This is the next set. So it is 4 divided by 2, total number of cache blocks divided by number of blocks in each set. Okay. So that is 2, that is nothing but 2 power 1. So 1 bit to represent the set. Okay. The remaining bits are for representing the tag number. Fine. So it is 4, 1, 2 is the address representation for the cache memory. Okay. So this solves the problem which is given. This is the problem. So we have seen all 3 different techniques. So students who are interested can just check how this addressing is done. I have taken a very small memory. Okay, so if I assume that in the first word or in the second block, I'm taking the second word, suppose. Okay, so you know that each block consists of some words. I have told it is 4 words here. Okay, so each block consists of 4 words. Fine. In the second block, if suppose I'm taking the second word, fine. So what is the address of it? This is 0, this is 1, 2, 3, 4, 5. Okay. So the main memory address will be 4 bits for the word. So 0, 1, 0, 1 for the word. And this is the second block. Second block totally it is 7-bit address. So as it is second block, it is 0, 1. Okay. 7, 0. Okay. So this will be the address to check this, to retrieve this particular second block, second word. Okay. It is the 5th word. so 101, and it is a second block, so 01. Okay, now this address, how it is mapped in direct mapping? In direct mapping, okay, it is okay, there are four words to, one second. Okay, you can see how it is mapped in direct mapping. One second, I will take four words. Okay, so it is four words like this. Fine. So this is the second word, second word in this particular block, second block. Okay, so second two is nothing but 10. Okay, and the main memory address, it is 7 bits, 2 bits for word, and the remaining bits are for the block. That is 5 bits are for representing the block, as it is 32 bits. 32 bits, it is 2 power 5. So 5 bits are for representing the block number. Okay, so 2 bits for word, 10, and it is the second block. So 0, 10. Fine. 5 bits is for the address, so 1, 2, 3, 4, 5. This is the address for retrieving this memory location. 2-bit word. Okay, and the second block, so okay, once again 0, 1 is this block. Yes, I will take this memory. Okay, so second 0, 1, 2. Okay, remember block numbering starts from 0. Okay, so 0, 1, 2, and this is here. So third block, third memory is represented by 10 because it starts from 0, 0. Okay, so this particular location, okay, so this is block 3. So in direct mapping, block 0, 1, 2. Block 2 modulus cache block. How many blocks in the cache memory? There is 4 blocks in the cache memory. Okay, so 4, the result is 2. The particular block, this block will be present in block 2. Okay, now how this address is mapped? 10 will be word. Okay, 01 will be the block number, and tag number is 000. Okay, so this is the mapping. What will be there? Each block consists of 4 words. So first 4 words is tag 0. First 4 blocks is tag 0. Next, from 5th block onwards, it is tag 1. Okay, so if you are trying to solve it, and if you didn't get, you can just contact me, whoever are interested. Okay, this will not be asked. Okay, this will not be asked in any question paper. Okay, for your semester exam. I just wanted the students to know. Okay, if you're trying to solve it, you can just contact me if you didn't get the particular word itself. Or if I take the 31st block, I take some bit. Okay, if you're trying it, if you're not getting, you can just contact me. Fine. So this is the 3 mapping, cache memory mappings. Direct, associative, and set associative. If there is any doubts and you have not got any understood any topic, you can just ask me. Any doubts in the mapping? Okay, we'll go to the next topic. We had seen in previous class, yesterday's class, about the replacement algorithm. Okay, now the next topic is any doubt with respect to replacement algorithm? Students who have got replacement algorithm as the topic can do a survey on this algorithms, FIFO and LRU. Okay, how the FIFO algorithm works, and you can demonstrate that also, how it is working. Okay, if you're not getting anywhere, you got stuck, you can just contact me. Okay, that algorithm working is not there in your syllabus, but it is nice to understand how the replacement is taking place. Okay, if you have no doubt, we'll just proceed further. Students who have got the topic replacement algorithm for the presentation, any doubts? Had you attended the class yesterday? Hope you had attended.
Yes, ma'am.
Any doubt in the concept?
Ma'am, there are not many information about this replacement algorithm, ma'am, on Google.
No. There is many information, or you can see the operating system textbook itself by Galvin. In that, there is the
Ma'am, there it's
demonstration.
only given about LRU, ma'am.
Yeah. There is a demonstration of how the working takes place. Suppose the cache memory. So, which suppose I place some data. Okay, I want to place a new data or a new block. Okay, suppose this is a block. So where it will be placed in FIFO, first in whichever has come first, this will be replaced by 4. So you can take a string of blocks. Okay, so you can take a string of blocks, any blocks which is being retrieved randomly, and see how the placing takes place. Okay, how which block is selected as a victim block for replacement. You can see such. This is just for FIFO. Okay, there is for LRU also the same similar technique. The blocks diagrams are there. You can search in Google or the textbook by Galvin.
Okay, ma'am.
Okay, if you want the textbook by Galvin, I can forward you. I think I have. Fine, you just go through Google. Yeah, it is a nice concept to understand. Any doubts, students? Okay. Shall I move further? Next topic. Shall I move to the next topic? Okay. Next topic is on performance. Okay, performance of a system. All of you know that the system performance is expected. Good performance of the system is expected. Okay, and it must be of it is ideal if it is of lower cost. Okay, good performance based on a higher RAM and a higher cache memory cannot be placed. It is not ideal because the cost matters. Cost of the system also matters. Okay, so performance depends on how fast the data is or instructions are being brought for the processor for execution. Okay, and also it depends on how faster the execution is taking place in the processor. Now this is very fast. The execution in the processor is very fast, but how the instructions are accessed from main memory, instructions and data are accessed from main memory or cache is means if there is a cache miss. Okay, data is not available in cache, so this process takes more time. Okay, so this time has to be increased. That is a issue. Okay, and there were many researches done on this, how to retrieve the instructions faster from the memory. Okay, so there were many researches which is still going on. Okay, so one possibility is the technique where interleaving is used. Okay, so interleaving means the data or instructions are not continuously stored in a particular place itself, in a particular block itself. Okay, so without interleaving, if the instructions are retrieved consecutively, one after the other. Okay, suppose green stands for accessing the memory, and yellow stands for retrieving the data and sending the data to the processor. Okay, so this is 3 instructions which is retrieved from the memory. And if I take that this is 1 clock cycle, okay, 1 clock cycle, 1 unit time of processor, okay, then here it needs 6 clock cycles to retrieve 3 instructions. Okay, so in one instruction, 1 clock cycle, the memory cannot be accessed. You had seen the row address has to be mapped, and then the column address has to be mapped. There is so much procedure. Okay, suppose we assume that in 1 clock cycle, the memory is accessed, the location of the cell is accessed, and the next clock cycle, the data is retrieved and sent. Okay, so if the instructions are accessed one after the other, it needs 6 clock cycles. Now, this is instruction execution in parallel, instruction retrieval in parallel by interleaving and storing the data. Okay, so we'll see how the data is interleaved and stored. So what happens here? Here, the first instruction is access, the memory location is accessed, the instruction data is sent or retrieved or returned to the process, whatever procedure. Okay, first instruction, first time the memory is accessed. Here the second memory is accessed. Okay, accessing the memory, sending the data or receiving the data, whatever procedure. Okay, this is the third instruction. Now here you can see in 4 clock cycles itself, that is, this process is done parallelly. First instruction sends the data, and here the memory location is accessed. Second instruction's memory location is accessed at the same time in the second clock cycle. Correct? Here also parallelly the work is being done. So if parallelly the work is being done, accessing the data, accessing the location of memory, and while some other previous instructions data is accessed and sent. Okay, so this task is done parallelly. When the task is done parallelly, in lesser number of clock cycles, all the 3 times the memory is accessed and data is sent. Okay, so in 4 clock cycles itself, you can see that the instructions are accessed, the memory is accessed, okay, and the data is taken. Fine. So that's why interleaving of memory is very important. Interleaving and storing the data is very important. Okay, now we'll just you can observe this. It is within the RAM. Okay, those are the different chips in RAM. Those are the different chips, and you had seen the cell structure. So in this chip, I had told that the cells are there within. Okay, and parallelly there is not only one cell here. You had seen there are a number of cells. Okay, and these cells are divided into modules or banks. You can see there are different modules, many modules in one single cell. Okay, each module contains number of cells. You can see there number of cells in each bank or each module. Okay, so it is divided into modules, and first suppose word 0 is here, the first word of block 1. The second word of block 1 is in the next module, and the third word is in the next module. Okay, so whenever I am accessing a particular address location, I am accessing a particular word. Okay, am I audible? There is some disturbance. Am I audible? Yeah, I think yes. Am I audible, students?
Yes, ma'am, you're audible.
Is there any disturbance? Okay.
No, ma'am.
Tell me if there is any disturbance. Fine. So here, one blocks different words. Okay, these words are stored in different modules. Okay, and these modules are accessed parallelly. So you can see here word 0 is accessed. Okay, that is accessing a particular location in memory. The next location, while retrieving this data, the next location can be accessed. Okay, so like this, there is uh, we say that it is divided, the memory is divided into modules. Okay, each module stores a particular word, the next module stores the next word of the same block. Okay, so if this type of arrangement is there, the data can be accessed parallelly here, like paralleling. Okay, here you're accessing word 0, retrieving the data of present in word 0, while next at the same time word 1 is being accessed. Okay, and word 1's data is being next in the next clock cycle, word 1's data is being retrieved, meanwhile word 2 is being located. Okay, and that memory is being accessed. Fine, so it is possible by dividing the memory, that is RAM chip, into number of modules. Okay, modules are accessed simultaneously. Fine, but there should be clash, like after it sending this data, then the next word is data has to be sent. Okay, not everything in parallel. Fine, yes, you can see this diagram. You can see this diagram. These are the modules. Okay, these are the modules, that is one word is stored here, the next word is stored in the next location. There are number of words. Okay, not only block 0, block 2's data are also in the different modules. And each module consists of ABR and DBR. ABR stands for address buffer register, and DBR stands for data buffer register. Okay, what is that buffer? You know, the term buffer means it is stored. Okay, storage place. So a buffering place, we say. So the next instruction or the next address, okay, is being stored there. So each module has a address buffer register and data buffer register. Okay, and you can see these modules, the modules are accessed parallelly. Here you can see the red line where the modules are accessed parallelly. Here this is module 0, module 1, and the next module. Okay, fine. So there is address buffer register and data buffer register. Address buffer register stores the address which has to be accessed next, and data buffer register stores the data. Okay, which is retrieved from that memory location, or which has to be stored in that particular memory location. Fine, it is successive. The words are accessed from different modules at the same time. Okay, at the same time means leaving a gap. Okay, so successively stored, successively the modules are accessed. Fine. Okay, so what happens? The average rate of fetching the words is increased. You would have seen here, when retrieving this instruction itself, only 3 memory access 6 cycles were required, whereas here only 4 cycles are required. Okay, so average rate of fetching the words in main memory is reduced. Okay, rate of okay, the time taken to fetch the words are reduced. The rate at which fetching of data is taking place is increased. Okay, so time taken to fetch the data is reduced. Fine. These are 2 ways of organizing memory into modules. Okay, so here the first method is called as high order modules. Okay, here in high order modules, module address is at the higher end. Okay, the module address is at the higher end, and in this particular technique only one module can be accessed at a time, whereas different addresses in the module can be accessed. Okay, the second technique is lower end modules, where the lower LSB bits, LSB bits of LSB indicate which module the data has to be taken from, and the address within the module is indicated in the higher bits of the address. Okay, the address in module, within the module, which address has to be accessed, that is indicated in the next higher end, in the higher most significant bits. Okay, in the most significant bits, the address within the module is mentioned. Okay, so using this particular architecture, by changing these modules, if there are 4 modules, so 00, first module is accessed. If the next address 01, the second module is accessed, 10, the third module is accessed, and so on. By changing the lower bit itself, okay, you can access different modules successively. Okay, and within the module, which address location has to be accessed, that is indicated in the most significant bit. Okay, in this technique of managing the memory, only one module can be accessed at a time. Within that module, different module addresses can be accessed. Okay, the other modules will be used for direct memory access and other purposes. Right, so here okay, so when block of data is transferred, only one module is busy at a time. Okay, whereas here several memory modules are kept busy at the same time. Okay, you can once again I will erase the lines. You can see the difference. The module indicating of module, that bit comes in the lower side here. So by just changing the last bits, once the address is changed for the last bits, you are able to access all different modules at the same time for the same address. Okay, and the address, if it is 00, okay, so in module 000 address is accessed. Again in module 1, 00 address is accessed. Module 2, 00 address is accessed. Okay, by just changing the lower bits, different modules, the same address of different modules are accessed. Okay, whereas here by changing the LSBs, okay, in the same module 000, same module, different addresses can be accessed. So only one module is kept busy in this particular structure, whereas here different modules can be accessed successively, okay, at the same time, almost at the same time. Fine, and thus increasing the speed of memory access. Okay, so that is about interleaving. If you have any doubts, you can ask me. Listening.